we'll continue with our lecture. So what we are going to do is we are going to learn how we can do speed control. And I think this is one of the important topics for you as a mechanical engineer, is how we can do speed control of DC machines. Now let's bring a new page and see what we can do here. So first, let's define what is meant by speed control. So what is meant by speed control first? So let's take real example. So assume that we have an elevator here. This is an elevator, and you are moving this elevator through a motor here. Here you have your counterweight, and you are controlling your motor here, and this motor is coupled with mechanically with the elevator. Now if we sketch the relation between the torque speed characteristic for the load and for the motor, so this load has a constant torque speed characteristic, which is mgr, and this motor, as we discussed earlier in this lecture, has a linear torque speed characteristic. So this line has an equation depends on the machine. So this value is VA divided by K phi, and the slope of this line is minus RA divided by K phi square. And this point here will be the operating point. This is your running speed. So your machine and your load will run at this point. This is omega, omega operating. This is the operating point. Now we need to do speed control. What is the meaning of we need to do speed control? So if this elevator is going between floor 3 and floor 4, you need at the beginning to accelerate, then you need to go with constant speed, and then you need to decelerate to stop at floor 4. So if we sketch the speed versus time, we start from rest, we need to accelerate, then go with constant speed, then we decelerate, and this is your start location, and this is your end location. So in all of our application, real life application, we need to do this. We need to accelerate, we need to go with constant speed, we need to decelerate. So we need to do some sort of speed control. So how we can do speed control if your operating point is single point here and it's constant? So we need to be able to move this point up or down. So moving this point up or down, this is what is called by speed control. So speed control means we need to move the speed up, so we are accelerating, or we need to move the speed down, so we are decelerating. Now let's sketch again this torque speed characteristic curve. So here is the speed, here is the torque, and here is our motor, and here is our load. Now, how we can move this point up or down? To move this point up or down, we can change the load, okay? So if you increase the load, you are lowering the speed. If you decrease the load, you are increasing the speed, which simply means you will ask people from the elevator just to step down so we can go faster. So this is not logical. So changing the load, this is not practical. So it is not practical to change the load characteristic, but what is practical is to change the motor characteristic, is to move the motor characteristic up and down. So if we can change the motor characteristic, we can do speed control. So speed control means we need to change the motor characteristic so we can change the speed of our motor and load, so we can speed up or speed down. Now let's see how we can do this. So if we go back to our torque speed characteristic, we have omega of the motor equal to VA divided by K phi minus RA divided by k phi all squared multiplied by t developed. This is our torque speed characteristics. So here is omega is our y-axis and t developed is our x-axis. So we need to change this characteristic. So what are the variables you see here? If you look at this equation here, you have omega equal C1 minus C2 t developed. How you can change this characteristic? So what are the variables you have here? So the variables you have here, you can change VA, or you can change RA, or you can change phi. Okay, so these are the control variables. So you can change VA, or you can change RA, or you can change phi. These are the control variables. You cannot change K motor, because K motor, if you remember, it's a P divided by N pi, and P is the total number of poles and N is the total number of turns. So you cannot change the constant of the motor. So we can do speed control by changing one of these, VA, RA, and phi. And these are the three types of speed control we have. So what are the speed control types we have? So the speed control we have are armature voltage control, which means we are changing VA. The second type is armature resistance control, which means we are changing RA. And the last type is field control, which means we are changing the flux. So these are the three types of control that we have. So we can do armature voltage control, or we can do armature voltage control, armature resistance control, or we can do field control, which are the three variables we have here: variable 1, variable 2, and variable 3. These are the these are the control variables that we have, and these are the three types of speed control that we can do for DC shunt machines. Now let's take one by one and see how we can deal with it. So let's start by armature voltage control. So keep in mind that we will start, or assuming we are at rated conditions, and let's see what is the flexibility we have. So we will assume in all the three cases, in case 1, in case 2, and in case 3, we will assume that we are at the rated conditions, and we will see what are the flexibility we have. This is the first assumption. The second assumption, that when we are doing one of the controls, the others will be constant. So if we are doing armature voltage control, all the two others will be constant. If we are doing armature resistance control, the other two will be constant. If we are doing field control, the other two will be constants. So whenever we are doing one of the controls, the other one will be constant. Okay. So let's see armature voltage control. So when we do armature voltage control, we assume that RA is constant and the flux is constant. So what we have our speed equal to VA divided by K phi minus RA divided by K phi all squared multiplied by T developed. And now let's highlight what is constant and what is variable. So here K phi is constant, K phi is constant, RA is constant. And our equation is between omega and T. So what you can do here, you can change VA. So if we sketch our torque speed characteristic, here is T, here is omega, and here is our characteristic. The starting point here is VA divided by K phi. The slope here is minus RA divided by K phi all squared. This means if you are changing VA, what will change and what will not change? So if you are changing VA, this part will change, but all the others will be the same, which means that by changing VA, the flexibility you have is just you can move this point. You can move the no load speed, but can you move this no load speed up or down? You can move it only down. Why? Because we will assume that we start at rated conditions. So if we are at rated conditions, we can just decrease our VA. Now let's see how this works. So here is our torque speed characteristics, omega t. Here is our rated condition, which I will sketch it in black. This is our rated condition. Now when we change our torque, our V armature, the curve starting point will change. So we can move down. So if this value here is VA rated, the other values will be VA1 less than VA, here VA2 less than VA1, here is VA3 less than VA2, and so on. But don't forget that the equation for the slope here is not function of VA, which means that the slope is constant. It is not function of your variable. This means when you are sketching these lines, all these lines are parallel to each other because they have the same slope. And you are moving from this curve to this curve by changing VA. Now if we go back and we sketch our load curve, this is the load curve, you can see that you can control the speed. So here you have omega rated, here you have omega 1 less than omega rated, here you have omega 2 less than omega 1, omega 3 less than omega 2, and so on. So as you can see that we can do a speed control by armature voltage control. But the point is you can control the speed only below rated speed. You cannot go with a speed above rated. You cannot go here. You can only go down. Why? If the machine is working at rated voltage, you cannot increase the voltage. You can only decrease the voltage. So to control the speed, from 0 speed to N rated, we can use the armature voltage control. So simply by changing the armature voltage, you can control the speed. But how we will do this, keeping our armature and the field constant? So if we have a battery here is our DC battery. What we will do, we will connect the field directly to the battery. Then we will add a device here called voltage controller. And this voltage controller will supply our armature. EA, RA, IA, V source. Now the current inside the field, I field, will be V source over RF. And V source is a battery and RF is constant, so IF is constant. The voltage going to the voltage controller is V source. The voltage controller will give you a voltage from 0 up to V source. How you are controlling this? You are controlling this through a control signal for the voltage controller, and usually we name this control signal the duty cycle. And this duty cycle can come from your microcontroller. So this duty cycle can be output from your microcontroller using PWM, pulse width modulation. And the duty cycle can range from 0 up to 1 to give you V out from 0 to Vs. So this is V output from the voltage controller. So as you can see that the voltage controller is only controlling the voltage seen at the armature. But the voltage seen at the field here is the voltage of the battery, which means that we are changing only VA, keeping IF as constant, and we are not touching RA. This is how we can do armature voltage control, so we can control the speed from 0 to N rated. So this technique is efficient because to reduce the speed, what you are going to do, you are reducing the input voltage, which means you are reducing the input power to reduce the speed. So this technique is efficient. But the problem with this technique is that you can control only the speed below the rated value. Now let's go to the next speed control technique. The next speed control technique is the armature voltage control. Armature resistance control. So the armature resistance control is based on changing RA. So we are changing RA. How you will change RA? By adding an external, resistance. So your RA new will be your old RA plus R external. This RA is the resistance of the wires, which you cannot change. This RA is the resistance of the wires. You cannot change this. So what you will do, you will add a variable resistance to the armature. So if we sketch the circuit here, here is our RA, which is the wire resistance. Here is our our armature, E armature, T omega, T motor omega. So what we will do, here we will add a variable resistance here, R external. So we will add an external resistance to the circuit. Then we have our field and you have our battery here. V source, RF, IF, IA. So as you can see, we're just increasing RA without changing the field current and without changing V armature, because V armature equal to V source. So by this connection, V armature equal constant, IF equal constant, and this is the condition for our control, that when we are changing one of the control variable, we have to keep the other one constant. Now if we go back to our torque speed characteristic curve, here is our torque, here is our speed, and this curve is the rated curve. This point here is VA over K phi, and the slope here is minus RA divided by K phi all square. So which will change with your RA? So as you can see, this value here is not function of RA. RA only will change your slope. Only your slope is function of RA. And when this value RA goes up, your slope will go up. So if we need to sketch the curve here, so all the curves will start from the same from the same starting point, but with different slope. So here is with R external 1, here is R external 2 larger than R external 1, here is R external 3 larger than R external 2, and so on. So as you are increasing your RA, your curve is going down. And if we sketch the load curve here, our load curve, this is the load, you can see actually you are reducing the speed. So this technique will control, so this technique can control the speed below rated. So why? Because this is the rated speed. So this technique can control speed below rated. So your control range will be from 0 up to N rated. But the problem is you are increasing losses. So your losses is going up. Why your losses is going up? Because you are adding a resistance, which means this technique is not efficient. So this technique is simple and cheap, but this technique is not efficient. That's why no one is using this technique nowadays. So back in time, they were using this technique because it's simple and cheap. And at that time, no one cares about the efficiency. There is surplus energy. But nowadays, because we care about the energy, we moved from resistance control to voltage control. So for voltage control, it's more complicated because you have a voltage controller and you have another controller to send the order for the duty cycle, but it's efficient. For the resistance control, you have high speed because you have high power. So what is the idea? To reduce the speed, let's lose the power. This is not logical. So if you need to reduce the speed, reduce the input, reduce V input. Don't add a resistance to take part of the load so you can reduce the speed. This is not logical at all. But this is one of the techniques that is used for speed control because of its simplicity, and its cost is very, very low compared to the other one. Now, as you can see from these two techniques, that you can control the speed just below rated. How we can control the speed above rated? This is our last technique. So the last technique is field control or field current control. So for field control, we will change IF, and IF will change phi. And if we are in the linear zone, if you sketch the magnetization curve IF phi, it will be linear. Then we have our knee zone, then the saturation. So if we are in the linear zone, a changing IF will have a linear effect to phi. So we will say field control here for a changing IF, not a changing phi. And we can say that the relation between IF and phi is constant. So if we go back to our equation that our omega equal to VA divided by K phi, we can write this as K motor IF. This K motor is different from K because the original was K phi, and we can write this as K2 IF because the relation between phi and IF, here we can write phi equal to K2 IF. Then we can take K2K and we can name this as K motor IF. So instead of writing K phi, we can write it as K motor IF minus RA divided by K motor IF squared multiplied by T. So this will be our torque speed characteristic, omega equal to VA divided by K motor IF minus RA divided by K motor IF all squared multiplied by T. And we will change here IF, this is our variable, is IF. So changing IF, as you can see, will change the starting point of the line, and it will change the slope. So if we sketch our torque speed characteristic here, here is the speed torque characteristic, and here we have our rated condition. This is the rated line. So this point is VA over K motor IF. The slope of this line is minus RA divided by K motor IF. Given that we start at the rated conditions, we can only decrease IF because we started at the rating conditions. Once we decrease our IF, this value will go up, and the slope will get higher. So the curve will go up. So this is by reducing IF. So by reducing IF, as you can see that the torque speed characteristic will shift up, which can give you speed above rated. So we can use this technique to increase the speed. So this can be used to have a speed above N rated. And because we are reducing IF, they call this field weakening. So we call this technique field weakening because you are weakening the field, you are decreasing the field. So decreasing the field will give you a speed higher than rated. So for the field control, we will reduce the field, we will take the field down, and taking the field down will give you an overspeeding. Overspeeding means your speed can be more than N rated, and this is totally fine because N rated is not the maximum mechanical speed that you can go. You can go in the speed higher than the rated, given you are not exceeding the maximum of the mechanical system. So N rated has no meaning. It's not the maximum speed that your mechanical system can withstand. N rated means if you apply the rated voltage to your machine, it will run at this speed. This is what is the meaning of rated speed. So rated speed doesn't mean the maximum allowable speed. The maximum allowable speed depends on your bearing and the mechanical system. So to overspeed, we will use field control. But how we will do field control, how to change IF keeping RA and VA constants. It's the same trick that we did for VA change. So what we will do, if we have the battery here, we will connect the battery directly to the armature. Here is EA, here is RA. So V source will be V armature. So V armature is constant. Then we will connect the voltage controller here, voltage control, and we will have our field here, field. So the voltage controller will have a constant voltage V source, and it will give you a variable voltage here from 0 to V source. In this case, your IF will equal to the voltage of the controller divided by RF. So changing V controller will change IF, but the idea is you can go with V controller from 0 to VS. So I field will go from 0 to I field rated. So when V controller equal VS, by design, IF will be IF rated equal VS over RF. And if you go with your field to 0, if I field is 0, your speed will go to infinity. Why? Because EA, which is almost V source, equal to K motor IF speed. So if IF goes to 0, your speed will go to infinity. So using field control, theoretically, you can go with a speed from N rated up to infinity and beyond. So using field control can give you this flexibility. We can change I field by inserting a resistance into the field, but I'm not suggesting doing this because inserting a resistance means lower efficiency because you are adding losses. So what we covered so far today, we covered 3 types of speed control. The first speed control is the armature voltage control. The second speed control is the armature resistance control. And the third speed control is the field control. The armature voltage control can be used to control the speed below rated. The armature resistance control to control the speed below rated. The field control to control the speed above rated. We will not use armature resistance control because it's not efficient, but we will solve some problems on this. So next